So we will continue our discussion in instructions by investigating the procedure calling. These are the steps required. First, you place the parameter in the registers. Second, you transfer the control to the procedure. Third, you acquire the storage for the procedure. Fourth, you perform the procedures operations, meaning the instructions. Fifth, you place the result in the registers for the caller. And the last step, you return to a place of call. And here are some of the registers that we need to know at this point. We already discussed the temporaries and the saved registers. Now, since we have a procedure calling, there will be a method or a class or a function where you call it, you go and execute the instructions inside the procedure, and then you return back to the caller. And because of this, you need argument registers. You have 4, A0, A1, A2, and A3. You need resulting variable registers, and you have V0 and V1. And you also need to save the return address after you finish the procedure, and you save it in the RA register. Now we know those registers. Also, this 0 register, we know it from our discussion last time. We also need the stack pointer to save the saved registers that you used inside the procedure. And you will see it in some of the examples. We save it in the stack, then we perform the procedure operations, and just before we return, we pop it from the stack and go back to the call. Now we are left with only few registers. We have the at register, and it's reserved for the compiler. We also have K0 and K1, and they are reserved for the operating system. And we have a global pointer register, and it's used for static data. And the last one is the frame pointer, which is pointing to the frame, and we are not going to talk much about it in this course. So we have 2 instructions now for procedures or methods. We have jump and link procedure, or the instruction jump and link, and after this you define the label that you want to jump to, meaning you define the handler of your procedure. So this jump and link, for example, if we use a C language, you'll have main function, and somewhere you will call a function, let's call it F1, and then F1 would be defined somewhere here. And when you convert this code to assembly, this line or this statement in the C code would be translated to jump and link, and then you will have the procedure label, which is F1. You can call it something else, but as long as you keep the same name when you call and when you define the procedure. Now, jump and link, it saves the address of the following instruction in the register RA, and then it jumps to the target address. Now we have the other procedure or the other instruction, which is the jump return, and you give it the return address, and this instruction is the equivalent of the return function at the end of the method. So we replace this by jump return, and you give it the RA that you already saved when you called jump and link. It's good to know that jump return, it could be used also for case switch statements. Now we will have an example where you have a leave procedure, which means that there is no call inside the method. So we call it leave example. It has those arguments G, H, I, and J, and it define the variable F, and then execute this statements, and after this it returns F. Notice that there is no call inside the leave example, and this actually what makes it a leave function. Now we assume that the arguments from G to J is stored in A0 to A3. Now we are using the A registers. So this is A0, A1, A2, and A3. F, we save it in S0. Now, since we are using S0 inside, we must save S0 on the stack. Meaning that at the beginning of the method, we need to push it in the stack, and just before we return, we pop it from the stack. The reason is this S0, it might be used before you come to this procedure. Let's say that you are coming from the main function, and in the main function, you were using S0 to do some operation. So to save the S0 that have been dealt with in the main function, probably the variable S0 or the register S0 have an important value. So when you go to the leave example, you push it in the stack, do the procedure, and in the procedure we used S0, so we must have changed it. And just before we pop it, so you have the same value of S0 just before you called it in the main function. And we also have the results in V0. So F, the value F should be moved to the register V0, and then we go back to the caller. To see this in action, this is the assembly code for that example. We already actually know this statement, and we discussed it before, where you do add instruction here, and then you do add instruction here, and after that you subtract this one from this one, and we use temporary value to help us with the calculation. And that's what we did here. This is the first add, this is the second add, and this is the subtract. This is the procedure body. Now notice we have first the procedure label, which is called leaf example. And then we have a column. Notice that in the main function, we must have an instruction, jump and link. And then we call this procedure. This way we come here. Also, jump and link, one of the job, it saves the instruction right after jump and link in the register R8. Now we came here. The first thing you notice in the procedure body, we used a saved register. We used only a single one, which is S0. So we need to save it. We need to save S0 on the stack by the push operation. To do a push operation, you need to understand that the stack pointer, when the stack is empty, it's pointing at the highest address. And every time you want to push, you lower the stack pointer by the size of the thing that you want to save. So we want to save S0, and we know that all registers are 32 bits or 4 bytes. This is why we push the variable by reducing the stack pointer 4 bytes, this one, this way, add immediate the stack pointer with the value -4. So this way we pushed the stack pointer down here and we made a space for a value. Now we store the value of S0 that might be important for the main function, if we say that this is the main, and we push it inside the stack pointer. The stack pointer and the offset is 0. This way, we have the S0 here. Now we do the procedure, we do the instructions that we need to do in our method, and once we're done and we get the final result, you must move the result to V0, because V0 means that this is the return value. To move it, we use the add with the 0. We use add the S0 register with 0. So we're just moving the content of the register S0 to the register V0. After this, we do the pop operation, and we do the opposite of what we did in the push. Notice in the push, we moved the stack pointer down, and then we stored the value of the register S0. Now what we do is we are doing the opposite. We are loading S0 from the position of the stack pointer. After we load, now we have the value of S0, we pop by incrementing the stack pointer. So when we pop, we go to the original stack, empty stack. Once we're done with this, the last instruction is the jump return, and you give it the register RA that you already saved when you use the instruction jump and link. So in summary, in any leaf example, you do pushing. First, when you write the procedure body, and you are not sure if you are using saved register or not until you finish the whole procedure body. And at that point, you know that you have certain registers. For example, we have the S0. Now you know that you need to push and then At the end, when you are done, you need to pop, and after that, you jump return with RA. And don't forget that you need to move the result, the final result, whatever is the final result, to VZ. So the leaf operation, the leaf procedure is fairly easy. Now, if the procedures are non-leaf, which are procedures that call other procedures, for nested calls, caller needs to save on the stack its return address and also any argument. So you will see when you are pushing in the stack, you push actually the arguments. Maybe you push A0, an A argument. Also, you push a return address, RA. So these you can see them pushed in the stack. And you also, when you restore from the stack after the call, you need to pop them. As an example, we chose a recursive call for finding the factorial of an integer n. Just to remind you, the factorial of n is n times n minus 1 times, you go down the numbers until 3 times 2 times 1, and that's it. This is the factorial. Now, to do this, what we did in this function, we say if n is less than 1, meaning if it is 0. If it is 1, 1 is not less. First, you choose a number, let's say 5. So if it is 5, 5 is not less than 1, you don't return. You will return once you reach to 0. If you reach to 0, then you know that 0 is less than 1, and you return 1. Otherwise, you still need to count the factorial. You need to still compute the factorial. To compute factorial, you go to the else. If we say that, for example, we need to get the factorial of 5, what happens? You go to else, because 5 is not less than 1, so you don't execute this. You execute the false path. And here we return n, which is going to be 5, times, and here we are calculating the factorial because you are multiplying every time. And then you give it, you call the same function, which is the factorial, and you give it n minus 1, which is 4. So to understand this, what happens is you called factorial n, and then factorial n won't satisfy this condition, so you call factorial n minus 1, and you keep calling until you are reaching factorial 1. And after that, because in factorial 1, you will come here, 1 is not less than 1. So you do the false path. And you keep calling, and this time you will call factorial 0. And when you go factorial 0 and you check 0 here, 0 is less than 1. This is true. And at that time, you return 1. So basically, you go through the green arrows. You call the factorial n, call factorial n minus 1, call factorial n minus 2, and so on, up to factorial 2, factorial 1, and then factorial 0. Now, factorial 0 will return 1 for you. Now, it says return. When you return back to the last called version of the method factorial or fact. And at that time, you have 1 returned here, and you already multiplied by 1, because when you say here in the false path, you say n times, and then you call the factorial. So you keep returning, and you can notice here that you have n, and here you have n minus 1. So if you have 1 here, you would have 0. If you have 2, you would have 1, and so on. If you have n minus 1, you would have here n minus 2. If you have n here, you have n minus 1 here. So if we substitute n factorial at the beginning, you will call n times factorial n minus 1, and this one will return for you n minus 1 factorial n minus 2, and then you go down the chain until you reach at the end 1 times factorial 0, and you know factorial 0 is equal to 1 times 1, and you keep multiplying because you are multiplying here until you reach to the end. This is the way the recursion happens. Now, it's important to know that we have only a single argument, which is an A0, which is at the beginning, it's the number n, and the result is saved in V0. Notice that we didn't define anything like the last example, we defined f, but here we don't define anything. So automatically, this value will be saved in V0. Now, in this table, this helps you when you are dealing with comparisons that have less than or greater than or equal, less than or equal, and greater than. So in our case, we have less than, which is this one. So the assembly, in the assembly, we have to get to have those two instructions, set less than, followed by branch equal. Because you will branch if the opposite condition is correct, which is when x is larger than or equal to 1. And this is true here. If we have anything larger than 1, 5, 4, 3, 2, you go to the false path, which is the path that you need to branch to. Even if you have 1, you also go to the false path, which satisfies this. So remember that we will use set less than and branch equal in our case. These are, if we have comparisons, this will help us in future examples. So let's try to write down the assembly code. You notice that first, we will try to push the RA and the A0, because this is a non-leaf procedure, and especially in this case, it's also recursion. So you must, from the beginning, before you know anything about the procedure, push the RA and the A0 in the stack. Now, since we are pushing two values, we need to drop the stack pointer by 8 bytes, 4 bytes for the first one and 4 bytes for the second one. Now, we calculate this part here, and I already told you that you will use set less than and then followed by branch equal, and this is what we have here, set less than followed by branch equal. When we compare with 1, and since this is an immediate value, we will use the version of set less than, that is set less than immediate, and we can compare those two. If it is true, then the value of T0 is going to be 1. And you know at the beginning, maybe you have the number 5 as example. So 5 is not less than 1, so this would be false. So this value is 0, and 0 is equal to 0. So you will jump to you will branch to the label L1. In L1, what you do is you decrement the value of n, which is the A0, and then you call the same method again, or you call the same procedure again by using jump and link, and you call it factorial. And this is the recursive call. So what happened if we say the A0 have the value of 5, meaning that n is equal to 5. So you will go 5 first, and then this condition will make you branch you decrement to 4, and then jump and link. You push the new RA and the new A0, which is at this point, it would be 4. And then again, you do it for 3, for 2, and also for 1. Let's check 1. When you have 1 here, when you compare 1 and 1, 1 is not less than 1. So again, you will call the factorial function. So you will keep calling until you reach to 0. Now, once you reach to 0, 0 is less than 1. So you will not branch. You will continue here. So what we are going to do at that point, we will add immediate 1 to the register 0. So you are moving the value 1 to V0, because now the return value would be equal to 1. And that's what we said in the factorial. In the true path, if we said if n is less than 1, in our case it's 0, after we went down 5, 4, 3, 2, 1, and now we reach to 0, at this point you return 1. So you return 1 this way in V0. Now, to return, you need to pop the last 2 values that you pushed. Be careful here. We pushed at every time we call the factorial for number 5, for number 4, for number 3, down to 1. Every time we call it, we push 2 values. So for 5, 4, 3, 2, and 1, these are 5 values. We pushed 10 different values. 5 of them are A's, and other 5 are the A's themselves, which is the 5, 4, 3, 2, and 1. So we pop the last 2 items representing the 0 and the RA of the 0. And you should have load them too. Notice that what we did here, we push by saying add immediate, store, and store. When we pop, we are supposed to say load, load, and then add immediate to pop. But those 2 values are not changed. So we are not, if we add the loads, it would be a waste of time. And that's why we take them out. And after that, what you do, you return this way, jump return RA. Now, when you say jump return, you return to the next instruction when you were called. Remember, when we were calling, we would say jump and link and then factorial. So when you say now jump return, you jump and return right here. So at this point, you keep returning every time. And that's what you will do when you return. You will load 2 values, the A0 and the R1, and then you pop them by incrementing the stack pointer. And every time when you do that, that's the core of your operation. You multiply the V0, which has the last value, and you multiply it by A0, which you just popped. And you keep it in V0. And after that, you would say jump return again. So when you jump return at this point, you will jump return to the one that was called before that. So you will return here, you will pop 2 values, and then again multiply, pop 2 values, multiply, and so on. And this is the way you do the recursion. Just so you remember what we said, notice that you jump and link, jump and link, jump and link, jump and link until you reach to 0. And at that point, you return with pops. You return with popping values. You return with popping values, and so on. And every time you return, you multiply. That's the way you do the non-leaf procedures. Now, the local data on the stack, a C variable has two storage classes, the automatic and static. The automatic variable are local for a procedure, like the S0s and the temporary values, and are discarded when the procedure exits. If you care about a certain value, like the S0, you should save it or push it in the stack at the beginning and pop it at the end. The static variable exists across the procedure, the whole procedure. They are declared outside all the procedures, and they use the word static in C, and I believe they use static also in Java. The stack is also used to store the variables that are local to the procedure, but does not or do not fit in the register, as we've seen in the last two procedure calls. Now, remember that the stack pointer, also the frame pointer, even though we don't discuss the frame pointer much, starts from high addresses, and when you want to push data to them, you decrement their values. So as you can see here, the stack pointer already here, and you saved many things. You saved argument register, you saved return address, you saved S registers, and some local probably array or structures. Anyway, you saved many things in the stack, and once you're done with the procedure, you're supposed to pop them, meaning you go to the high address again, so you increment the stack pointer. The local data allocated by the callee, which is the procedure that called the function. For example, automatic variables. Also, the procedure frame. When we say the procedure frame, it's something related to operating system called activation record, and they are used by some compilers to manage stage stack storage, but that's outside of the scope of this class. The memory layout, you should know that the stack pointer is when the stack is empty, is pointing to the highest address, and then it is decremented. There is something called the dynamic data, or in the operating system, they call it a heap, and it works the opposite of the stack. So stack go to the high address, and when you push registers or values in the stack, you decrement the pointer. When you pop them, you increment the pointer. In the dynamic data or in the heap, you are in a lower address, and you want to push, you increment the pointer, and when you want to pop something from the heap, you decrement. Also, we have static data, and if you have static data, even though we didn't have any static data in the previous procedures, you use the global pointer to point to them, and this is the program counter. The program counting can start from this place, and any instructions or any procedures, the main or any classes or methods, supposed to be written in the text part. So the text is the program code, the static data global variables. The dynamic data is called a heap. They used, for example, some of the functions is called malloc that allocate some memory space, and you use the new declaration in Java when you want to have a new type or a new method. Whenever you say new, this means that you are working in the dynamic data. And the stack is automatic storage, as we described here. Now we will move to communicating with people, which means how the character data is represented in the hardware or in the computer. So we have ASCII codes that represent 128 different characters. 95 of them are graphic, meaning the capital letters starting from A to Z, the small letters from A to Z, and also the numbers from 0 to 9, and also the special characters. And they have also 33 control, like the escape, the delete, and many others. And in Latin one, that's another encoding protocol, and it has 256 characters, which is the ASCII, the 128, plus more graphic characters. And we have the Unicode, especially the after some historic development, we reached to the UTF-8, UTF-16, 32, and 64, and these represent the English letters and probably all the languages known to, or the current modern languages known to man. You can represent them in those two encoding methods. Now, the instruction that we need to add to deal with characters, we have the load and the store, but now, previously, we have the load word and store word. We always work with the 32-bit as a whole. But now, since we have characters, and we know that the characters could be only 8 bits, meaning 1 byte. Some characters need 2 bytes, which means that it's a half word. So now we need instructions to deal with this. We have load byte unsigned, and store byte. And they work the same as we described the load word and store word. But now this is for byte, and this is in case you want to be unsigned, and this is for storing. Similarly, you have 3 more instructions, but now for half a word. So the load word, store word works for 32 bits. The load byte unsigned, and store byte, they work with 8 bits. And the half word, load half word unsigned, store half word, they work with 16 bits. So they could use bitwise operation easily. The MIPS byte, half word, load, and store is, as you can see here. The string processing is a common case. When you say load byte or load half word, it's sign extended to 32 bits in RT when needed. The load byte unsigned, it's 0 extended, so we don't care about the sign. And the store byte, the store just rightmost the byte or the half word. Here's an example. If you say that you want to convert this C code, which is a string copy, you are copying the string from an array Y to the array X. So what happened? You define an index and you go through a while loop. If, or what you do, you copy the Y to X. Notice that Y is an array of characters, and you are copying to X member by member because you have an index I, and every time you increment I by 1. You stop the while loop when the Y or the X, because you are assigning here, when they are equal to the end of file, or when they are, or this character means that they are equal to 0. When the character is 0, then you are done. So as long as you are not equal to 0, it means keep copying and keep incrementing the index. Here we assume that the addresses of the X and Y, which is this one and this one, this is not assumption. You should do that actually, because now they are arguments. So X must be A0 and Y must be A1. And we have I and S0. Since we are using S0, now you know that you need to push it at the beginning and pop it at the end. And this is the assembly language. So we pushed the S0 and we popped the S0 at the end and followed by jump return. Now, inside what we did, first we have I equal to 0 since it is written here. So to do that, we use the add 0 register to 0 register, and this is, of course, it's 0. This way we assign the value 0 to the S0 because we will use the I as an index, and we start from 0 and then we keep continuing. Now, you notice here that we have X of I, which is an array with an index. And if you remember what I said about arrays, you have to do 3 operations. The shift left logical, followed by add, shift left to increase the index by 4. And you add the index after you multiply it by 4. You add it with the base register of the array. Now we have A0 and A1. After that, we use the load or the store. Before we had load word. Now we do that, especially the shift left logical, because we are working with words, meaning 32-bit. But if you are working only with a byte, then we don't need to do this. And this is in our case, these are string copy, and these are characters, which is simply 8 bits. And this is why we don't have to do this. We just do an add followed by load to get X of I and similarly get Y of I. What we do here, we copy the Y into the X. So we need to prepare the Y first. And this is what we did. We have A1, which is for the base register for Y, added to S0, which is the index. At the beginning, it's 0. And we put it in a temporary value. And then we load byte unsigned. So we load this character into T2. And now we're done with the Y in the temporary register T2. We do the same thing, but now instead of A1, we are using A0. We have it here. Now we will have the T2 that we already loaded. We will store it into the X. We will store it into the X. And now we did the copy by those 4 instructions. Now we need to check if we need to branch or not. You can check here that we are using not equal to, which will be the opposite in the assembly, meaning that we will use branch equal. So we check the T0, the T2, sorry. If it is equal to 0, this means we will branch to L2, which will finish the work. But as long as it's not 0, we didn't reach the end of file, and we keep doing the loop, meaning we will decrement the value of I by add immediate S0 with 1. We are incrementing actually the value of I, and then jump to L1 to continue the loop. Notice here that we begin the I with 0, and every time we increment I. When do we finish? When we reach to the end of file, when the character, the last character we look at is 0 or end of file. And this is the string copy example. Now, here are other things that we need to be aware of. What happens when we are dealing with a 32-bit constants? If we have a constant that big, we can move it from one place to another using the load upper immediate. So if we have this 32-bit, first we get the 16 upper bits. At this point, they are 61. If you looked at this binary, in decimal, they are 61. So we load it into S0. After that, we do the OR immediate between the lower part, which is at this point 2304, with the S0. And we will have the value in S0, the combination of both, which is this value, the total, the whole value here. So most constants are small, and 16-bit is enough. If you need 32-bit, then you need load upper immediate followed by OR immediate. You copy the 16-bit constant to the left 16-bit of the RT, meaning S0 at this point. So you have this first, and then you clears right 16 bits of RT to 0, which is this one. And after that, now you have this in register S0. You do the OR immediate between the S0, which is this one, and this value here. When you do the ORing, you will end up with what you see at the end here. Okay. Now we will talk about branch addressing and also the jump addressing. We talked about the branch and the jump before. What we care about now is what to write in the immediate value. So the branch instructions specify opcode to register to compare if they are equal or not equal, and a target address, or what we call the offset. Most branches target are near the branch, meaning that you branch forward or you branch backward. In loops, usually you go backward. If you have an if statement, you branch forward. We call that the addressing here, or dealing with the offset, is BC relative addressing, meaning the target address is related to the program counter. So you say it's the program counter plus this offset times 4. Notice that the program counter at that point, when you are executing this instruction, it's already incremented by 4. The reason it's always incremented by 4, because what we want for any program, if you have instruction 0, followed by instruction 1, followed by instruction 2, and so on, you start the BC here. We know that every instruction is 32-bit. So you start the BC right here, and then you add 4, meaning that you are adding 4 bytes to go to the next instruction. And then add another 4 to go to the next instruction, and so on. So automatically, every time you are executing an instruction, while you are doing this instruction, for example, the program counter already is working, or it's adding 4 to it itself to go to the next instruction. So we have the BC already incremented by 4. So we have this BC, and we take the offset and multiply it by 4, and we add it to the BC. Remember, to multiply by 4, you are shifting to the left 2 positions. So that's for the branch. For the jump, what you do, it's a pseudo direct jump address. What happens here, you go to the BC and you take the 4 most significant bits. Bit 28, 29, 30, and 31. And you concatenate it with the jump address, which is the 26 bits that you see in the J type instruction. So you have from 0 to 25. If you see here, we have 4 bits and 26 bits. Sorry, 26 bits with 4. This is equal to 30. And we know that we need 32 bits for any data and also instruction. And this is why we multiply this address, the 26 bits, by 4, meaning we add or we concatenate 2 more bits to the right. So we are shifting this one. We are shifting the address of the jump to the left 2 times. And this way we have 28 bits, 26 bits from the instruction itself, and 2 more zeros that we add, and we concatenate it with the BC from 28 to 31, which is 4 bits, and this is give us a total of 30. So basically, in the branch, it's BC, the program counter, plus something. In the jump, we concatenate only 4 bits of the BCs with this whole address shifted to the left. To give you an example of how this help us write the assembly code, the loop code from earlier example, if you remember, we had a certain loop like this one. We did the shift left and add, load, branch equal, branch not equal, add immediate followed by a jump, and we had an exit here. Let's try to find it in previous slides. If we go back, it has a loop, and it was before when we worked on this loop here. This is what we had, and we described this before. Now we will have the same code. For example, here we have 2, and we have jump, loop, and exit. That's what we have also here. Two, jump, loop, and exit is the same one. So you can go to the video and listen to the description. Here we care about what is the value of the labels. What is the value of the loop? What's the value of the exit? What's the value of this one in the jump instruction? And so on. And what is the value also in this exit? So what happens, the shift left logical, we have T1, S3, and also we have 2. The shift amount, we know that this is R type, so this is the shift amount. The 9 and 19 is the T1, the S3, and this is the opcode with the functionality. And we know that the RS is 0 in the shift left logic. Here it's already have been discussed before, and we can fill it this way. Notice that we started this loop at the location 80,000. So we started at this location. The next instruction is 4 more bytes. The next one is 4 more, so it's 8, and then 12, and 16, and then 20, and then 24. So the instructions go like when you write the instructions or when you translate from assembly code to machine code, you are moving 4 bytes every time. Now, the load could be translated to this or this way, and we described this before. Now, in the branch not equal, we have the label exit, and we need to find what is the value of the exit. So we know in the branch, it's BC relative. So you will have the BC, which is currently pointing here, which is BC plus 4. It's already incremented and it's here. And you want to have the BC plus wherever you want the exit to be. The exit was here. So you need to add 1 to move from here to here, and another 1 to move from here to here. So you need 2. And that's why we write, instead of this exit, we write 2. Another way of looking at it, if you not need to write down this number and you are trying to figure it out, check where is the label and see how many jumps you did in the machine code. So you did 1 and then 2. Remember, you start from the next instruction. That's 1 jump and then another jump. Or let's say that this is 1 hop and then another hop. 2 hops, so you write 2. And this is what we mean by BC relative. Because first you look at where is the program counter, and from that you start counting. Now we continue looking at the next instruction. It's add immediate, and we can convert it to machine code and take this as an practice for yourself. And we already have so many examples before. Now the last one is jump loop. Where you want to go in the loop is here, right here. So we know that the jump, we shift to the left by 2 bits. That's what we did in the concatenation right here. And because of this, what we need to write here is, where is the label? This is the label that I want, loop. And you check what is the address of the label, and then you divide it by 4 to get it to 20,000. Now, if you look at it the other way around, if you are reading this instruction, or if the interpreter is reading this instruction, jump to loop, he will, the machine code is actually 20,000. It will be shifted to the left by 2 bits, which means that it will be a double 2 times. So it will be 80,000. So basically, to find this number, start from the BC location and hop 2 times, or wherever is your label. And to get this number, check where is your label, address, location, and then divide it by 4 to get the correct number. Now, branching far away. If you are trying to branch, but here you are limited to 16-bit, and you want to branch, this L1 was really far away, somewhere that needs more than the 16-bit offset. So L1 at this point, this instruction, L1 cannot be represented in the 16-bit. So work around this problem. You could convert the branch equal to branch not equal. And this way, what you say, if what you wanted, when they are equal, you go to this far away location. Now here, if they are not equal, you will jump to L2, which is, you just continue normally. You continue to L2. Otherwise, which means that when they are equal, you will jump. You use now the jump instruction. You jump to L1. And now, if they are equal, you will jump far away. And now you have more flexibility because you have 28 bits to put the label. And this will make you jump really far away. Now, it's good to know the different addressing modes. There are some of them that we used in MIPS. I will start with the one that we used. We used this one, which is the immediate addressing. We used this kind of instruction, and this is what we call the I tag. We also used the base addressing, meaning that we have a base register and we take the offset or the displacement or the constant, the immediate value, and we add it to the base register to access the memory. And we use this when we talked about the load and store. We have also a BC relative addressing, and this is what we did in the branch, whether it's branch equal or not equal. And we just explained this, that we take the BC, and we already know that the BC contains BC plus 4, which is the next instruction, and we add to it the address that you have here. And this is called the BC relative addressing. The pseudo direct addressing, which we used in the jump, we don't add, we concatenate. We take some bits from the program counter, and we take the bits from the offset. Sometimes it's shifted or not, and we chose to shift to the left by 2 bits. So now we had this, also this one, and the immediate. The last one is the register addressing. And the register addressing, we have a register that points directly to a register somewhere in the register file. And that's normal. When we want to find RS, you go to the register and find it. Similarly for RT and RD. There are more addressing modes, but these are the ones that we used in the MIPS. Now we will talk about translating and starting up a program. What happens if you have a C program, the compiler converts it to assembly language program, and then the assembler will produce for you an object file, which will have the machine language module. So here we have program written in C. After the compilation, we will have the assembly instructions. The assembler will convert this assembly to machine code, meaning that this means that the object will have zeros and ones. The linker will take the objects from your code, the one that you write, after the compilation and the assembling, the assembler, and it will add to it or link with it any library routine that you defined in your code. In the C language, we use include at the beginning to have libraries and use an already implemented methods, classes, or functions to our code, and we link it this way. In Java, I believe you use import, and some other language use the word use to call the libraries. So this is what happens. You have a linker and it links both of them, and it generates for you an executable file that could be run. And at the end, we have the loader that loads this executable file into the memory, so it's ready for processing. Now, this way of linking is called static linking. We will look at other subjects, but the whole section here is related to the operating system and software more than hardware. There are assembler pseudo instructions. We know that when we want to move a variable from, or move a value from the register, for example, from register T1 to T0, we use add with register 0, and this way you moved it to the other register. There is another instruction which is called move. So you move the content of T1 to T0. But this move is a pseudo instruction. So you cannot convert it directly to machine code. What you do, you convert it to its equivalent, and this one, you convert it to machine code. Because if you look at an opcode for the move in the MIPS, ISA, you won't find. Similarly for the BLT, which is a branch if less than. This is the set less than followed by branch not equal. You could rewrite this as you can see here. You take the L, you take the T1 and the T0 here, and you call it, you will branch if they are less than, if the relation between those two is less than. So you set less than. If these are less than, you will set this one. So if this is true, this would be 1. And then if this is 1, you will branch. If they are not equal, you will branch to the label L. Here we say branch if less than. So if they are less than, you will branch. Now, noticed here we use the register AT, or the register at, and this at register it's reserved for the assembler or the compiler, and that's what we set in the register table. So we used it here. When you are working with pseudo instruction, you use the at register. Now, producing an object module, the assembler or compiler translate program into machine instruction. It provides the information for building a complete program from pieces. There are many things, and I suggest you read your book for details. There is a header, a text segment, static data segment, relocation information, sample table, and debug information. The header describes the content of the object module. The text segment translated instructions or the assembly code. The static data segment is the data allocated for the life of the program. Relocation information for the content that depends on the absolute location of the loaded program. The sample table is the global definition and external references. You keep them organized in a table. The debug information for associating with the source code. Now, after we produce the object module, meaning we produce this object, so we have the assembly, and now that we have the object, we will move to linking. Linking object modules, you produce an executable image, you merge segments, resolve labels. If you have label troubles, then you need to resolve it. Basically, what you do here, you determine their addresses, and then you patch location dependent, any location that are dependent, and external references. You could leave location dependencies for fixing by a relocating loader, but with virtual memory, no need to do this. The program can be loaded into absolute location and virtual memory space. But to understand this, we need to talk a little bit about virtual memory, and we will push this subject later, so you don't have to worry about this. This is for another course. Loading a program after you did the linking. To load the program, basically, you load from the image file or the hard drive, the disk, we say the disk too. You load that, the program, into the memory. And the operating system courses, if the code is reside in the image file or in the disk, they call it a program. If you move it to the memory, it becomes a process. So you read the header to determine the segment sizes, you create virtual address space, you copy the text and initialize that into the memory, you set up the argument on the stack, you initialize all the needed registers, for example, the stack pointer, the frame pointer, the global pointer, etc. And then at the end, when you are ready, you jump to the main. If you are working with C, even with Java, they call it main, you jump to the startup routine. And since it's a routine or procedure, you have arguments, you have a return value, and you use the stack pointer to push first, and then you bump, and we discussed this before. We talked about the static linking. We have another idea which is called the dynamic linking. In the dynamic linking, you don't link everything. You only link or load library procedure when it is called. So if you have a code and for some reason you didn't call the library or the procedure at all because of certain conditions, you don't load it. You only load it when it is called. It requires a procedure code to be relocatable. It avoids image bloat caused by static linking, too much objects for no reason. Automatically picks up new library version, which is good in case you are working with servers. The lazy linkage, what you do is you have to distinguish between the first call and the subsequent calls. So we are working here with the dynamic linking library or the DLL, and I'm sure you looked at files that with extensions .dll. Those files use the dynamic linking, and in the first call, there's a lot of work to do, or there's some work to do. The subsequent calls, you can take out some parts. And this is what we mean by the lazy linkage, meaning that it's like you are lazy, you don't want to do the full job. Anyway, you have an indirection table where first you have the text, the instructions are here. So notice that you have jump and link and you go somewhere, and then you have jump return. You have certain variables that you need to go to the data, and then you go to another code where you do some work, and then you jump to another text, and then you jump to another text. It depends on what happens. Here, you have indirection table. You have load, or you load the routine ID, and then jump to the linker or loader. And then here, the linker or loader code. Here, this is the dynamic linker code. It's dynamically do some mapping codes here. And it's like those two prepare this piece for you. So now it's ready. Whenever you have this instruction, you jump right away, right here. And for details, you can go to your text that describe this in detail. Now, if you want to check what happens in Java, Java program, it has a compiler, and it produces for you the assembly code. It is called in Java bytecode, which is the class bytes. Now, you also have Java library routines that you import in your code, and the Java virtual machine interprets those bytecodes and give you the or take the compile Java methods and generate the executable for you. Notice we have here the just-in-time compiler where it takes your Java bytecode and generates for you the machine language or zeros and ones. Once you have the zeros and ones here, you have also the Java bytecode and the machine code for any library that you imported. You create the Java virtual machine from those three. Anyway, the job of the just-in-time compiler compiles the bytecodes of hot methods into native code for host machine, while the Java virtual machine interprets the byte code. The just-time compiler, or the JIT, they call it JIT, compiles those hot methods. But the compiler here, it's a simple portable instruction sets for the Java virtual machine. So it gives you just the Java bytecode. Now, this is a C sort example to put everything that we worked on together. We will talk about the swap function first, and then we will use the swap function in the sort method. This is a big example, and after that we will discuss many related things to this code, and we give you more information about other ISAs, but we will leave this for another video.